Hey everyone, here are the answers for the Hardy-Weinberg calculations on page 139. If you need to, go ahead and push pause and check your answers. Otherwise, I will be going through and explaining how to do the calculations for all of the questions 1 through 8, on page 139. Okay. So, starting with question number 1, and I'm going to do this on a separate sheet just because there's limited space on the page itself, but you are welcome to follow along on that page. It says the frequency of two alleles in a gene pool is 0.19, that's capital A, and 0.81 lowercase a. Assume that the population is in Hardy-Weinberg equilibrium. We're going to calculate the percentage of heterozygous individuals in the population and calculate the percentage of homozygous recessive. So for part A, well, actually before even all of that, the information that they gave us for that dominant allele, and because they used the word allele in the word problem itself, the frequency of the allele, they're talking about P and Q. That's something that students will sometimes have a little bit of trouble identifying is, are they giving you the genotype or the alleles? So the alleles are P and Q just by themselves, and then genotypes will be the homozygous dominant, heterozygous, and homozygous recessive. So for P, we are given 0.19, and for Q, we are given 0.81. Now to calculate the percentage of heterozygous individuals in the population. So for part A, what we are doing is heterozygous frequency is 2 times P times Q. So I'm going to go ahead and substitute these values in to where they go in the letters. So 2 times P times Q. And then when you put this into a calculator, you get 0.308. And in the word problem, since they were asking for a percentage, be careful with that, you're going to take your frequency and multiply it by 100, and that's where we get 30.8% for part A. For part B, they are asking for the percentage of homozygous recessive. So homozygous recessive would be Q squared. So I'm going to take Q and multiply it, and I get 0.656, but again, it is asking for a percentage. So this would be 65.6%. Okay, so there are your values for question number 1. For question number 2, the allele for wool is dominant over white wool is dominant over black wool. In a sample of 900 sheep, 891 are white and 9 are black. Calculate the allelic frequencies within this population, assuming that the population is in Hardy-Weinberg equilibrium. And keep in mind that these that are white, these 891, you can't tell if they're homozygous dominant or they're heterozygous. They're just white. So we don't start with the dominant phenotype, we start with the recessive. So in this case, your recessive phenotype is your Q squared. So Q squared is going to be equal to 9 out of 900. And then when you plug that into a calculator, you get 0.01. Now that is your value for Q squared. What we're looking for in order to be able to calculate the allelic frequencies, so calculate the allelic frequencies in your population, we're looking for P and Q just by themselves. So P equals, Q equals, and so in order to solve for Q, I got to get rid of the square. And I can get rid of the square by taking the square root. And whatever you do to one side of the equal sign, you've got to do to the other. So Q is going to equal to 0.1. Now I can take that Q and plug it into this equation. So P, once I plug in that value of 0.1, I can see that P comes out to 0.9. Those are my allelic frequencies, not the genotypic frequencies. That's what they were asking for in this problem. Number 3, in a population that is in Hardy-Weinberg equilibrium, the frequency of recessive homozygous genotype of a trait is 0.9. sorry, 0.09. Calculate the percentage of homozygous dominant for that allele. So they're asking us to solve for p squared. So basically, p squared equals question mark. We were given q squared. We were given the frequency of the homozygote genotype is 0.09. So now to solve for, in order to get p, I need to know what q is, because then I can take p squared. So I'm going to take the square root. Always try to start with that q squared if possible. That will get you the ability to take the square root and solve for p. So q is equal to 0.03, which means that p is equal, when you plug it into this same equation, p is equal to 0.7. Then you can take that number and plug it into this value, so p squared equals 0.7 times 0.7, and that is 0.49. But the question is asking us to express it as a percentage, so I multiply that by 100, p squared is equal to 49%. Final answer. All right, number 4. In a population that is in Hardy-Weinberg equilibrium, 38% of the individuals are homozygous recessive for a trait. In a population of 45,000, calculate the percentage of homozygous dominant individuals and heterozygous individuals. So they're basically asking me for p squared, and they're asking me for 2pq. So they give us that 38% are homozygous recessive, so q squared is equal to 0.38. Sorry about that. Q squared is equal to 0.38. So now what I'm going to do is I'm going to solve for q, and I'm going to do that by taking, again, the square root, and I get q is equal to 0.6164, which means I can plug it in and solve for p by subtracting this from 1, and I get 0.3836. Now I can take that p and plug it into these values here. So p squared is 0.1471, and 2pq pardon the silence, I'm entering this onto the calculator, and I get 0.4729, but remember they're asking for a percent, so this becomes 14.7%. This one comes 47.3%. Now on this type of problem, so if they asked you to take it to a population, they didn't ask it here, but if they asked you to find out how many actual number of people there were that were affected, you would take this number and multiply it by the number of people in your population, which we will do later on. Number 5. Allele T is the ability to taste over a lowercase t. 400 university students, 64 were found to be non-tasters. Calculate the percentage of heterozygous students. So we're looking for 2pq, and then don't forget you want it as a percent. That's the heterozygous. So we're going to start with our non-testers. That's q squared, and 64 out of 400 were found to be the non-tasters. So 64 out of 400, that comes out to 0.16. Now I'm going to take this and take the square root to solve for q. Q is equal to 0.4. Plugging it into the Hardy-Weinberg equation, if q is equal to 0.4, then p is equal to 0.6. Now to get the actual number of, or percentage of people that are heterozygous, I'm simply going to take 2 times p times q, and I get 0.48, but they asked it as a percent, so my answer is 48%. Number 6. A rare disease is lethal, occurs in a population at a frequency of 1 in a million. Calculate the number of individuals in the town having of a population of 14,000. So this one, you do have to take your percentage and multiply it by the number of people. And since they say that it's expected to carry this allele, carry the allele, means that they're basically looking for the number of people out of 14,000 who are heterozygous, and that's my 2PQ. So that's basically what I'm going to look for, is how many people out of 14,000 are heterozygous. So they gave you the frequency of the recessive genotype, the homozygous recessive genotype is 1 out of a million. Okay? Now, what I'm going to do is take the square root, Q is equal to 0.001, and if that is Q, then P is 0.999. Now to calculate the frequency of heterozygous, I'm going to do 2 times P times Q and then I get, oops, very low frequency of, so 2PQ equals 0.001998. However, that is the frequency itself. Now to find out how many people out of 4,000 would have this, I'm going to multiply these two numbers together. So out of 14,000 people, if that's the frequency of carrier, how many people are going to be carriers? So I'm just going to take that number, multiply it by 14,000, and I get 28 when you round, because you can't have part of a person. So 28 is the number of people who would be carriers in this population. We're going to do a couple more of these in class as a warm-up, so I hope that this video helps you guys. Thanks for watching.